Okay, good morning, everyone. Happy Wednesday. Welcome to today's webinar on novel heat pump applications for new construction and retrofits, January 29, 2025. What could be a best way to end January with a heat pump discussion? This webinar was developed in partnership with the LEARN program. The LEARN program is a San Diego-based workforce education and training program that has partnered with New Buildings Institute and the Advanced Water Heating Initiatives to offer free energy efficiency and electrification webinars. If you're interested in learning more about the LEARN program, please do visit their website. The information is right on the slide. What was the first thing that came to your mind when you heard about this webinar or the title of it? Novel heat pump applications. Whenever there's a new technology, I think the first basic question that usually comes up is like, why move to something new when you already have a traditional or a conventional approach already in hand? What is that is lacking in this traditional approach that might drive us to make that switch? And given all the theoretical information you have about the products, like from the product range, specifications, manufacturers, suppliers, what happens when all of this theoretical information is integrated into practical applications? What really happens when you get into the field? When you integrate these technologies into existing buildings, in new constructions, what happens then? What are the benefits that we might achieve? What are the challenges we come across? And what could be a strategic approach to overcome any of those challenges? We are going to dive deep into a very detailed discussion about this and a lot more. And for that, I have an incredible team of panelists. Please join me in welcoming Tristan Grant, Associate Director, Codes and Policies Team from New Buildings Institute. Tristan has a background in building science and sustainable design. He has been in this field for almost 10 years. His expertise lies in renewable energy sector, high performance building and building performance design consultation, energy modeling, and gut rehabilitation of multifamily residential building projects across Northeast. Joining Tristan is my second panelist, Peter Pollard from KW Engineering. Peter has been in this field for almost 3 decades. His technical expertise lies in implementing energy efficiency improvements in buildings across diverse sectors, industries, and facilities. Joining Tristan and Peter is the final panelist of the day, Jordan Dens, Vice President, McGrath Associates. Jordan has been a consultant and technical advisor for over 2 decades to a wide range of stakeholders, including architects, suppliers, building materials manufacturers, contractors, developers. His focus lies on electric demand response, building and residential systems, and also as well as factory-built active housing, and also improving the building energy efficiency. The common thing about all my panelists is that they have a wealth of knowledge, and they're very eager to share it with you all. So please keep your pen and paper ready in case you want to take some running notes. But rest be assured, we will be sharing all the slides as well as the recording of this presentation right after the webinar. I'd like to welcome my first panelist, Tristan. Tristan, of all the recent interactions we have had, I can confidently say that as much as you enjoy and are enthusiastic about building energy efficiency projects, I think you're over enthusiastic about sharing the information with a wider audience. So let's have this opportunity and let's deep dive into what exactly is about novel heat pump applications and why even talk about this in the first place. Over to you, Tristan.
Thanks, Vidisha, and thank you all for joining us today. The idea for this topic has been kicking around my head for a while and was born out of what I've been seeing on projects I worked for in the Northeast, a lot of projects in New York City, New England, and surrounding states and cities. I work primarily in the high-performance multifamily affordable housing space. So these are projects that often are required to be electric and are going for high-performance certifications like Passive House. VRF has been the kind of default electrification pathway for a lot of these projects, and that's for a lot of reasons. It meets the design requirements of LIHTC financing agencies. They provide occupant control for heating and cooling. They don't take up too much space, so they can fit into tight, compact urban environments and urban lots. but there's also some criticisms and drawbacks of VRF. And, I saw some of those as well. Among that, there's emerging data on real world performance of VRF, both from an efficiency standpoint, but also from a leak incident standpoint. When the refrigerants leak, the systems don't go down, they don't operate, but there's also global warming concerns with that because these refrigerants are have high global warming potential, much worse than carbon dioxide and other emissions. And additionally to leaks, there's also just a high embodied carbon load with these VRF systems. They typically have large, long line set lengths. There's a lot of refrigerant in them. When you compare them to some other systems, they have higher embodied carbon. And when those systems and there's also changing refrigerant requirements when these line sets penetrate more than 2 floors. And so those upcoming requirements complicate VRF applications for some building typologies. Our next webinar next month is going to be focusing on that topic of the changing refrigerant requirements. So if you're interested in that, we'll get into that in more detail during that webinar. Next slide, please. So in addition to those drawbacks, VRF just also have some limited applications, right? For existing buildings, they can be hard to use because there are space constraints of existing buildings. It can be hard to bring the refrigerant lines down to where you need to install the indoor units in existing buildings. And there's also just some, optimized space use considerations and concerns. You have limited roof area with dense urban lots. That roof area can sometimes be better used for things like on-site solar or human occupancy. And like I said, when these systems go down, the entire line of connected indoor units goes down, which means you have multiple apartments, multiple spaces that do not have heating and cooling. Next slide, please. And so when we're talking about alternatives to VRF and talking about new heat pump solutions, there's a number of design, kind of macro level design considerations that we're looking at. One is the first costs. These systems need to be able to be cost competitive with the other equipment on the market. Second is operational costs. They need to be able to compete with the operational costs of other heat pump systems, and in some cases compete with the operational costs of fuel-fired systems. And we want these to be similar in operational cost to whatever it's replacing, right? We want to minimize the energy burden wherever possible, which is the amount of money that folks are spending on their utility bills. So with that kind of high level framing, I'm going to hand it over to Peter and Jordan to talk a little bit more about these constraints and how different solutions are plugging the gap here.
Thank you, Tristan. I know we have a lot of case studies to deep dive towards the end of the session, but I have a quick question for you from one of our participants here. They want to know, Emma wants to know, how does affordability equation balance out for high performance, multifamily buildings, affordable housing, and these new technologies?
Yeah, well, affordable multifamily housing has actually been in many states on the forefront of high performance design, and that's because of LIHTC and federal affordable housing tax credit financing processes. So they're often required to do above code performance design things like electrification, use high performance technologies and meet high performance design criteria like passive house. So they're getting financing is contingent on that, but there are still considerations to balance out in how you optimize and make them efficient enough so that they still have low energy bills and things like that.
Thank you for that answer. There's also another question. Since you were talking about VRF, David wants to know, how about VRF retrofits? VRF retrofits replacing boilers.
I guess specifically about what with VRF retrofit replacing boilers? They, like I said, existing building retrofits with VRF can be difficult. They range from, I would say, tricky to very tricky. Getting the refrigerant into the places that you need can be difficult if you're not able to run it on the outside of the building, depending on the size of the building. Boilers often boilers take up a relatively small amount of space compared to the capacity that they can deliver. And so VRF are sort of compact, depending on who you ask. So I think VRF can replace boilers, but there are a lot of considerations.
Thank you, Tristan. I think we are going to deep dive into the considerations and the cost factor towards the end during the panel discussion. But thank you so much for the presentation and setting the stage for the discussion. I'd like to invite my next panelist, Peter Pollard. Peter, since Tristan has set the stage for all the new technologies, what got the market barriers, I think we can deep dive into some case studies.
Hey, thanks. And hello, good morning, everybody. Thank you for taking the time to join us. I wanted to start with just a quick broader intro. I'm just an engineer, personally committed to helping to decarbonize existing buildings, focused on existing buildings. I have a team of like-minded engineers, and we're looking to do our little part to counter the reality of climate change. We have many customers, publics, privates, all kinds, who looked to us for how to do it, roadmaps, and what to start right now. So this talk is about something that's to start now, but I'm focusing on one of the tough scenarios. Someone brought up boilers. It's a common challenge, and this is about how we approach it. So as we see, my mantra is start with your building, not your boiler. I'm going to talk about the 3 steps there. Again, this is more about process than product. And we're focused on the types of buildings that use boilers, burning gas in boilers to make hot water and distributing hot water for space heating. As an engineer, I like to define exactly what I'm talking about here. There's many other situations where heat pumps apply extremely well. This is a particular situation. That's a tough one. And it's tough because for various reasons, it's generally expensive to simply convert such boilers to heat pumps as they exist. So this is about how to take action now to save costs now, and in particular to really reduce the cost of boiler conversions to heat pumps when that time comes. So I'll talk about these 3 steps: recommissioning and distributed solutions, and what I call hybrid resilient solutions. So next slide. This is really the bottom line of the concept here. I'm more or less going to read it to you. I apologize. This is a bottom-up approach to decarbonizing, again, existing hydronic, it's a fancy word for hot water, heating systems focused on zone level optimization, combining central and distributed solutions, leveraging existing infrastructure. And all this is about working with the real world constraints of existing buildings, addressing the very real temperature and capacity gaps between gas boilers and their standard heat pump replacements. This is about zone-specific solutions before big central boiler system investment, and again, actionable now with moderate investment. Next slide. Since I'm the California person on here, really, California is a great place for heat pumps. I think we all know heat pumps extremely energy efficient. They're proven and clean, not polluting. But it's, like I said, not a simple swap from gas boilers for these buildings. California, great place. Mild climates, clean power and getting cleaner all the time due to regulation, and advanced building codes. So great in many ways for heat pumps, but also an expensive place to do this. Electricity keeps getting more expensive and likely to trend upward. And it's an expensive place to do projects too. So, yeah, next slide, please. So, yeah, it's not a simple swap to heat pumps. So just quickly, the little picture of a couple gas boilers there, I tried to more or less scale this. It's a fairly classic installation of 2 boilers. These have a certain capacity through 3,200 kBTU, making 180-degree water. Very simple, very straightforward. These are also, typically redundant. Again, boilers small and relatively cheap, so there's very often a redundant capacity. So you normally just run one boiler, and you have a whole second boiler as backup, or for really peak need conditions, really cold days. you know, the size equivalent on the right, more or less, is an air source heat pump. Of course, it's outdoors. This one's only making 1200 kBTU, and the water's only 120 F. So it's great technology. It's common, but you know, burning gas is super easy, and it's just the whole pollution part that bothers us. So, and to match that, if you just simply approach this as, oh, we're going to install these heat pumps to match the existing gas boilers, then just click twice, please, Vidisha. Then, you know, to match that capacity, in fact, you need 3 of these heat pumps. Just click through, Vidisha, and then again, they're still not making the temperature. So, so these are, you know, these kind of conversions are costly. There's a lot of size and power issues and weight potentially. They're custom engineered, so hard to get them justified right now. Even some of the richest and most climate ambitious companies we work with here in the Bay aren't going that way yet. So next slide. So we want to start with the building, not your boiler. I'm going to talk briefly about this because we think of the boiler. I like to think of each zone. Zone is the fancy word for individual spaces in a building served by the heating system. And those are really the customers for a boiler system in the central boiler system. So this whole approach is about minimizing the peak demands and the high temperature demands in certain critical zones throughout your building. It's about getting really familiar with those customers, as it were, in a given building. Next slide, please. So as I said, the first step is recommissioning buildings for heat pumps in particular. And you know, we do a lot of recommissioning, retro commissioning, ongoing commissioning, all of these controls and relatively low cost adaptations, changing operationally how a building runs. We always save energy. We can certainly save gas right up front. And this approach, though, is going beyond that and continuing to adapt a building for future electric pumps. So really driving down peak heating needs to reduce the capacity of heat pumps you need, and driving down the temperatures. With heat pumps, you can achieve those high temperatures, but you need extra stages, and that just adds cost and space and everything else. So this is going that extra bit to recommissioning your building for heat pumps. Next slide, please. And so what I mean here is really applying a systematic methodology to identify, using data analytics preferably, critical zones, and then deal with those zones in particular as far as you can. By data analytics, I mean this is, you know, assuming a building with a BAS, and there's some data from zones, rather than say an approach which you can do things like just steadily reducing the temperature of hot water going to heat a building until someone screams, and go address those cold people, and hopefully do it on the coldest day of the year. It's a bit of a smarter, more systematic approach to using actual data to really understand what your zones are doing. Next slide. So this is just quickly to illustrate this, and I know that the legends are really small. So this is a sample dashboard from our software called KW Link, which is built on SkySpark, which we use for doing data analytics. And this is just an example of over multiple months showing the heating and cooling loads of different zones. And the point here is you see the wide variety of those faint lines. Some of these zones need a lot of heating, some need cooling. You know, there's overlap often. So this is really about identifying where the critical zones are. Next slide. And this is really just up to emphasize that you need to be tracking. Again, this needs to be a systematic methodology. It's not just about asking the chief engineer to play with temperatures and stuff. You really need a methodology to take this as far as you possibly can. Next slide. So that's a great solution. You know, no matter what, you want to dial in a building and take that relatively low cost as far as you can go. You're only going to go so far. You need to start upgrading in your critical zones. How are you going to address those zones that tend to be cold, or that drive your peak heating needs? The classic one is to install bigger coils. Coils are they're basically the radiators. They are radiators, and that's where the heat from the hot water gets distributed into a space. So putting bigger coils in throughout a building is a very invasive and very expensive project. You can do it. It's practically, if it's a gut rehab situation, definitely that's kind of the classic way to do it. In a new building, you just build it this way. In new buildings, go ahead, build it all electric, no problem. You build it with all the radiant heating and what have you that can handle the temperatures out of heat pumps. But for existing buildings, we again focusing on critical zones. So you can install bigger coils in those areas. There's also putting out there the local heat pumps. The illustration there is essentially a mini split. People are familiar with that. Requires an outdoor unit. Certain applications. And Jordan's going to talk about some other cool product and tech that it can effectively check that box. Those individual heat pumps too are relatively inexpensive. Prepackaged little pieces as opposed to larger custom engineered central systems. So the numbers do add up. I want to quickly note also that with the conversion to LEDs, certainly here in California, we've got a lot of buildings with lighting circuitry out there with a lot of capacity in it. They tend to be built from the start with a lot of excess capacity, 3 to 6 watts a square foot, very typical. And now with LEDs, you're using 1 or something. So there is a lot of capacity in those 277 volts. I'm not saying I've been able to do that yet, but I'm looking for an application just to mention it. There is distributed electric capacity, which is a big deal for major heat pump applications that potentially can be used out distributed into the zones. How's my timing? Next slide, please. Whew, this is fast. So you go through those first 2 steps as far as you can and see what, based on a particular building, the costs and technical possibilities of what you can do for central heat pumps varies quite a bit. And so maybe you'll get there, maybe you won't. And hybrid resilient solutions is about keeping some gas boiler capacity. And most, our customers, 2 years ago, many didn't really want to hear about that. Of course, everybody wants to cap off that gas line and make a showcase building. And I get it. But to maximize your decarbonization per dollar, we try to argue the 80-20 rule. The little graph here is trying to illustrate 2 scenarios, A and B, that maybe cost about the same dollar investment. And in scenario A is spend the cost to get one building to 100% electric, get rid of all the gas use, including in the peak conditions, the coldest days, and you'll achieve that level of greenhouse gas savings. And a scenario B is following this approach, keeping some gas boilers potentially for peak needs, and with the same dollars, you can likely get over 2-3 times the carbon savings because across 3 buildings. Sorry, the green squares are trying to illustrate spend the same money to get 80% there across 3 buildings instead of just one showcase building. Think about it. There's a huge resilience aspect to this as well. Mitigating risk. We've lived that. Well, here in California, folks know what PSPS sounds like, it means. Maybe elsewhere they'll be learning it. So that's public safety power shut off, which started a few years ago with the big fires initiated by electric failures, essentially, that we're all paying for now. But so those are events where the power is deliberately shut off to certain areas for 3 days, maybe a week or something. And in those cases, some people will be happy to still have some gas heating capacity. I'd also say, not a California thing, but certainly in our Utah office, we've seen issues with cold weather conditions where sometimes, you can have a problem with your heat pumps and you want to have a backup. And it's something to think about. So hybrid resilient solutions, maybe not where we all want to go long term, but as an intermediate thing, I think there's a lot of folks are pretty interested in this these days. So I think with that, next slide summarizes, and I look forward to any further questions either here or always reach out to discuss any of these. You can scroll on through, and I'm finished. Thank you.
Thank you so much, Peter, for that informative case study insights. On the question of like using a hybrid solution or even going in for an electrical upgrade, how often do you come across these situations like, understanding how much electrical upgrade would be required, and then how do you navigate through these upgrades, the cost, and trying to find an intermediate solution?
Yeah, at this point, it's there's a lot of feasibility study in each individual building. So these are existing buildings that they were built around gas boilers and easy hot water. So it depends on what's there electrically. There's a lot of variables to what's possible for upgrading gas boilers in an existing building. So the classic engineering answer is it depends. But overall, the hybrid resilient path, I think actually the resilient side is what's engaging people the most. I will also say quickly, these are difficult situations where you have a portfolio. It makes sense to start elsewhere with electrifying, with package units, gas packs and such. These things certainly in California are relatively more straightforward. So hopefully that answers your question a bit.
Thank you, Peter. I do have three other questions in the Q&A chat box, and I'm just going to pick one. Do modern gas boilers still not require any electricity? For example, monitors, controls, etc., to operate?
Yeah, that's a great question. Very important. Yes, I mean, I'm assuming if the power is down, that this is, especially critical facilities, there's backup generation. You do need some power for sure for a building to keep operating. And the heating system, it's not so much the boilers themselves. They need some electric for controls, but it's more like fans and such that still need to operate. But to be clear, that's much less power than is needed to run a heat pump that's doing the actual heating. So even though heat pumps are super energy efficient, it's a lot more energy and much more demanding to put in backup generation. For example, and when I say backup generation, not just a diesel backup, but we're building solar microgrids and such to provide backup, and that's just a lot easier with gas burning.
Thank you, Peter. And there's some interesting questions here. So sorry, I'm going to pick a few more, and I'm going to combine these questions. Two of our attendees want to know, in case if you're keeping a gas scenario, does it include upstream leaks? And the second question is, how do you prevent a buildup of mineral deposits in the hot water panels?
Yeah, I'm not sure what you mean by upstream leaks. I mean, obviously, using any gas still in that gas network, we do see it as a kind of an intermediate term solution. We ultimately want to go away from that. So, sorry, what's the second question then?
It's about how to prevent buildup of mineral deposits in hot water panels.
Uh, what kind of deposits? I'm sorry, I don't. Yeah, mineral deposits in hot water panels. So I think
Sometimes,
a little
yeah,
out of scope of what we're talking about here. Yeah,
sure. No.
you need to maintain the water treatment in your hot water system.
And there is one question on the cost of remodeling and retrofitting a building versus demo and building a new building. So it's
Yeah, I
like,
think Tristan's typing in there. So
right.
I think, there's dollar cost and then there's carbon cost, right? Embodied carbon. And that's what we're also trying to focus on, is some of these look difficult enough that, it's almost, it's feels easier to just rip it out and start again and build an all electric building. But there's huge embodied carbon significance to that. Don't get me started. So yeah, I mean, it's a reasonable question, but big difference. What we're talking about is a whole lot less than a new building.
Thank you so much for that, Peter. I think we will carry forward this discussion during the panel discussion Q&A. But I'll move forward to our third panelist, Jordan Lenz. Jordan, Peter has already set the stage with a lot of insights from case studies, and I think you can move this forward.
Thank you, Vidisha. Good morning, afternoon, evening, wherever you are. It's a pleasure to be here to speak to you about some work we've been doing over the past few years in alternative in heat pump retrofits. Peter says he's an engineer, only an engineer, or I'm not even that. I'm an architect, so bear with me. I will do my best. Next slide, please. We've already talked a bit about why heat pumps. I just wanted to kind of revisit this for a second here. Why are we talking about heat pumps? They're an efficient means of electrification. Today's heat pumps can fulfill the heating loads that we encounter in buildings almost anywhere. They're reliable, quiet, comfortable, and there are a lot of options and more options coming out every day. Next slide, please. And there are some drawbacks with heat pumps, and Tristan already covered a lot of these, so I'm not going to repeat it, but you can see the list here. There's quite a challenges with particularly retrofitting existing buildings. Next slide. So what I want to do today is talk to you about 4 projects that we have been working on for the past few years and are currently still underway. These are all demonstration projects conducted in New York City with the cooperation of various state agencies, particularly NYSERDA, which is the New York State Energy Research and Development Authority. And they're all alternatives to the traditional VRF approaches for retrofits. Note that because these projects in New York, it's a heating climate primarily, and low ambient heating and defrost meltwater disposal are some of the key challenges that we've encountered with these technologies and criteria for these products. And also note that these projects really are intended to assess the performance of the heat pump retrofits. They don't include envelope measures, which in a full retrofit, you would want to focus on those, of course, to minimize your load as a first step. In these cases, we want to look at a before and after scenario, comparing these heat pumps to the prior systems, and so they don't include envelope retrofits. Next slide, please. So the first case I'm going to talk about is the heat pump with no outdoor unit. Next slide, please. So you may have seen this product before. It's been out for a few years, and actually overseas and in Europe, it's similar products have been available for some time. This particular product is the Epica HPAC 2.0. The new models are called AIO, but it's a similar product. The heat pump is no outdoor unit, so its installation is minimally invasive. It's a package system. It hangs on the wall inside of the home. So there are no refrigerant connections, and it's a room-by-room system with small openings to the outside. Next slide, please. So we demonstrated this, or in the process of demonstrating this product in an apartment in a building in Queens, New York. See the building on the upper left side. We did one apartment to start off with. And in this case, we use an existing air conditioner sleeve to install the heat pump and use the opening of the sleeve for exchanging air with the outdoors for the heat pump's outdoor unit, which is inside the unit in the apartment. You can see the floor plan on the right where the yellow stripes are is where those units are installed. Next slide, please. So this is the installation. You can see the old air conditioner. It's removed. There's a plate put on the wall onto which the heat pump is mounted on a rail or a cleat that it's hung on. There's one large opening for air to come in and one to go out. That exchanges air over the heat exchanger inside the unit. And there's also a drain that goes through at the bottom. You can see at the bottom right. And the existing air conditioner grill is still in place. That did not have to be changed at all. Next slide, please. So here's some conclusions from this demonstration. We just concluded the work. The data is currently being analyzed from the 1 year of operation. It was a simple installation. We just did one apartment. We did not have to touch the rest of the building. We did need to remove the existing radiators, baseboard heat in that building to fit the units in. So there was some minor plumbing work, some minor electrical work. Overall, the resident was very satisfied with the cooling. However, note that when we switched to heat pumps, and these are forced air equipment, and residents are used to having a radiant-based heat system. They're not used to the drafts or the air movement that comes with a forced air type heating system. So especially in a colder climate, it's a little adjustment. They may not be as comfortable with that air movement. And this particular tenant did report drafts, so to speak, in the heating season. We have some cost data here per square foot, and a little bit higher than we would have liked. I think we're still figuring out how to install these units more inexpensively. $16.75 per square foot for this apartment, about a 600 square foot apartment. Because we're using electric, which is a higher cost of fuel, we have a slight increase in energy over the course of the heating season. Next slide, please. So moving on to the next case study. This is the mini split that slides into a PTAC sleeve. Next slide, please. So here's some fun pictures. These are mini splits stacked up on balconies on a building on the left. I think we prefer to have something like we have on the right, which is a little cleaner and safer, so to speak. Next slide, please. So with this product, this is a relatively new product from Fujitsu. It's a one-to-one mini split. They've basically taken their mini split and they've reconfigured the outdoor unit to be a more cubicle shaped and designed a custom built sleeve for it, which replaces the existing PTAC sleeve. Next slide, please. And so there you can see what it looks like in the finished state. It's a one-to-one system. Next slide. This is what the sleeve looks like. It's a custom sleeve that replaces the existing sleeve. It's insulated on 5 sides, and it has special feet and a pan with a heater to keep the water in liquid form in the base. Next slide. Here's a demonstration site in Brooklyn. It's a 4-story building. You can see the PTACs on the left. You'll notice the one that I've circled in red there. You'll see an extra little line going from below that PTAC sleeve opening to the gutter. That's where the drainage goes. So that's how we're dealing with the drainage at this site. You can see that in the upper middle picture as well. The old PTACs there on the bottom. Owner was having a lot of problems with maintenance and comfort complaints with those units. They break down often. They're constantly having to swap them in and out. They have a whole stack of spares just for that purpose. So they're looking forward to getting something that was more reliable and require as much maintenance. Next slide, please. We do have some preliminary data based on utility bills so far for this site. They've been installed for about 3 years now from the initial installations, and with really very good performance in terms of minimal to no complaints and hardly any, if any, service requirements. The red are what they call the split terminal heat pump. That's the Fujitsu product's name. And the blue is the old gas-fired heat pumps. Annual heating and cooling electric use is on the top left. And so the electric use for the split terminal heat pumps is slightly higher than the gas PTACs on average, which is not surprising because these run only on electricity and there's no gas. Of course, the gas use for the PTACs is 0. So the upper right graph shows the lack of gas there, and we only have gas for the PTACs. The cost is on the bottom left. You can see that the red units are in the same ballpark or a little bit less than the old PTACs. And of course, emissions on the bottom right are significantly lower given the grid mix in New York City. Next slide just averages those out. And so total cost annually for the apartments with these PTACs are $133 or 26% lower than the old gas units, and emissions 2/3 lower. Note that this was just a limited utility analysis survey of a handful of apartments. We're doing a much more in-depth analysis of monitored data over the next year on these installations. Next slide, please. So conclusions from this site. Yeah, these products are basically mini splits. So they do require refrigerant line work, but they're very short and fully internal to the apartment. You can do one apartment at a time, which is how we're doing it at this site, because the previous units are all packaged and apartment unitary systems. It's fairly simple to just swap out whatever apartments either are vacant or need replacements. Again, very minor electrical and plumbing work. Residents have been satisfied. These heat pumps are much quieter and more comfortable. And the owner is satisfied with the reduced maintenance. We've got some energy savings, and overall 15-year costs to the owner are slightly higher, or total cost rather, slightly higher than the gas P-tax, but when you factor in the reduced maintenance, which we haven't calculated in yet, it's probably much lower for the split terminal heat pumps. Next slide, please. Okay, number 3, heat pump that plugs into your hydronic distribution system. Next slide. This is similar to what Peter was talking about, which is the air-to-water heat pump to swap out for a boiler. And that's what we've done in a building in the Bronx with this AirMech system. It's serving the existing radiators as well as a DHW service. It's a little bit different than what Peter showed because we're in a colder climate. We need higher temperature water. And so there's a 2-stage system or a cascading heat pump system with a booster in the middle there that's boosting it's a water-to-water heat pump that boosts the water from that 80 to 90 up to 176 for delivery to the terminal units. Next slide. This is the building. It's 38 units. And we put the equipment in the existing, in a space in the basement next to the existing boiler room. Just outside of that, the outdoor unit was placed within about 15 feet. This building was originally a steam building that had been converted to hydronic with gas boilers. And now this is the electric conversion. Next slide. Here's some pictures from the boiler room. I won't get into the details here as we don't want to run low on time, but it's quite a complicated installation in a retrofit context to put this in. It's not simply plug and play. There's a lot of electrical service considerations and upgrades that went into this project as well. Next slide. So, wrapping this one up, it's definitely non-invasive for the residents. All the work's in the boiler room, but it's extremely complicated. It takes a long time, especially when you're dealing with the utility and getting them to upgrade the service. That's expensive. And we are expecting an increased energy cost, but we have not turned it on yet. So we will be seeing that over the next year, what that actually is. I'd say this is probably on par with the cost of a VRF, maybe a little bit less. So we're still, it's still an alternative in some situations. Next slide, please. Last one I want to talk about is the heat pump that pops into your window. Next slide. These are the new saddle-shaped cold climate air source heat pumps. They slide into the window, as you can see in the upper right picture there. These are a couple different manufacturers that we've been looking at and have done some, been involved with some measurements of their performance at a site in Queens, New York. Next slide, please. These were developed in part through a RFP that these New York State agencies issued to encourage the development of a product that they could use in New York City public housing. After having experimenting a lot with a lot of these other products, including VRFs, and finding them too invasive and too expensive. Next slide, please. I'm going to speed up here. So this is what they look like on the outside. We've got a couple dozen apartments that have these installed for about 1.5 years now. and been monitoring them and observing their operation and talking to the residents. Next slide, please. Here's the installation. There's a kind of a bracket that goes on the windowsill. These slide over the windowsill, and then you close the window, and there's some gasketing. They install in less than an hour. 2 people, semi-skilled or maintenance people can put these in very quickly. No electrical upgrades needed. Next slide. They cost about $3,000 each. They plug into a standard wall outlet. We did have to remove the radiator, so there's some plumbing work there. It does affect the operation of that window, of course, having the heat pump in there. Next slide. Just real briefly, we did look at the electric demand, and they are really not having a huge impact on that relative to the previous demand profile. Residents have been very happy being able to control their units. Some of them think they're a little big, but most of them are pleased with their appearance. Saw that comment. There's less overheating, and what we're seeing is that even though they're installed just in the bedrooms and living room, they do warm the entire apartment in this particular demonstration site. Next slide. So wrapping this one up, low cost, easy to install, residents happy. Obviously, it's not for everyone. It's a specific application here. You might not want to put this on your historical building. There's some constraints with window size and wall depth. It does affect the window operability, although in this site, they are planning to replace the windows with special windows that are configured to accommodate these, and that'll solve that problem. Next slide. I think that's my last one. This just wraps up the utility savings and costs for each of these 4 sites. I won't go over this right now. You'll have that in the slides if you choose to get them. Next slide. That's it for me.
Thank you, Jordan. And we have some questions ready for you. One of them, I'm not sure if it really falls within the scope of this webinar, but one of the attendees wanted to know if there was any workforce challenges with installing these heat pumps.
That is a big issue with electrification. But these products reduce that, with the exception of perhaps the AirMac system that I showed, or not the specific AirMac, but just the air-to-water system. The others are much simpler to install than your typical VRF system, especially the first one and the last one. But yeah, you've hit on an issue that is definitely on a lot of folks' minds. Having the people to install these unitary or package systems, I think take a few steps towards addressing that issue.
Thank you for that answer, Jordan. David wanted to know if Epoca has an AHRI certification yet.
I believe they do. I believe they do, yes.
And Edward wanted to know your thoughts on the comparison between Fujitsu split terminal heat pump versus the ice air package terminal heat pumps.
What was the second one?
Fujitsu and ice air package terminal heat pumps.
I'm not familiar with the second one you mentioned. ITAB?
Ice air.
The
Ice
ice,
air. Oh,
the
ice air?
yeah.
I have not seen a comparable ice air product. I know the ice air has a product similar to the Epoca, but I have not personally used that product, so I wouldn't want to speak about it.
Sure, no problem. Michael wanted to know, why was there like in a 15-year cost slightly higher for a split terminal heat pump than a gas PTAC? Do cost savings not pay back the initial cost?
They do up to a point, but not completely. So the PTACs are about $1,000 each, whereas the split terminal heat pump installed is about $4,300. So over 15 years, you can make back most of that, but not all of it. But we haven't factored in the maintenance cost, as I mentioned, which I think will more than make up that deficit.
Sure. Thank you for that, Jordan. Do any of these reports or case studies are published? The ones that it's for all the panelists that they have mentioned about the case studies, are these published and accessible?
Ours will be published when they're finished. Most of them are still either undergoing monitoring or just concluding. There is an article on the split terminal heat pump in a magazine that came out last year, which covers the results that I showed. So that is available.
Thank you for that.
I wish I remembered the name of it off the top of my head, but I don't.
That's completely right. We can share that in the email later.
Okay.
Attendee Nick wants to know that of all the pictures that have been shared, they show an atomized condensate drainage. Is that working in cold weather? And has there been any concerns?
That was a very key development. There were some hiccups along the way, but both of the manufacturers, both the Gradient and Midea manufacturers of those saddle heat pumps, have them working and working well. So it's really a key technology that allows those to be installed in cold climates safely and without requiring a lot of work to manage drainage. And I believe Epica has a similar technology that they're building into their newer models.
And are those models launched?
I'm not sure about that.
Okay. And there's another question for lowering the energy cost. Does this data confirm, like within the case study, that the energy cost overall would be lowered?
Well, for my case study, some of them it is lower, some of them it is not. So it depends what your baseline is.
And there is one more question for the saddle heat pumps. Do you know if the saddle heat pump manufacturers are planning on making different form factors to accommodate different window sizes?
Different window sizes?
Mm-hmm.
Not that I know of. They accommodate, I think, window sizes about, oh boy, I know that there's some folks from Gradient on the line. Maybe you could put that in chat. 29 inches, something like that, maybe a little less, 26 inches. So anything bigger than that.
Thank you for that. And I know Tristan did answer that question in the chat, but there was something about the residents paying a high energy cost during this ongoing case study. Would you like to throw some light on that?
Which case study?
And the one that you mentioned during your presentation, there were some upfront costs and the overall energy costs that were slightly higher.
The first one, Epica. Yes, that was $250 for the year. Was our projected cost in their total energy expenditures. In this case, the resident was a new resident starting a new lease in a building that was centrally heated. So their lease was adjusted so that they were paying for their heat, whereas the other residents in the building were not paying for the heat. So it's not like they were paying all of a sudden more. It's just that it was a new situation for a new tenant.
And some additional context there is that I believe this was in New York City, right, Jordan?
Yeah.
Yeah, and so New York City has regulations that owners of multifamily affordable housing buildings have to pay for the heat during the heating season. And so that's kind of a separate tangential design consideration with a lot of different electrification technologies. But when costs do increase with any of these, that's borne by the owner.
Thank you for that clarification, Tristan. Tristan, would you like to throw some insights from some of the case studies that we were going to talk about earlier?
Sure. Do you want to back up to those slides?
Sure, definitely.
And so I have some additional case studies from some projects I was working on before I came to NBI that are looking at basically that are looking at these technologies as market ready solutions. And can you go to the next one actually to start with? So 136 140 Croton is a multifamily affordable housing project in Ossining, New York, which is a small city, small town, a little bit above New York City. This is a wood frame building. They're actually using the ice air cold climate packaged thermal heat pumps, very similar to the APOCA units that were presented today. They have two slightly bigger 10-inch rounds rather than 8-inch round penetrations. Because this is passive house, they have a special improved, like thermally broken, improved air leakage sleeve for the system. But this is a passive house US design certified project. And there's been testing to show that they should be able to pass the air leakage requirements. So these technologies are seen as cost competitive to what else is out there and able to meet pretty strict requirements and design constraints for high performance design. If you want to jump to the next one real quick. Similarly, New Penn is an 11 building distributed development in Brooklyn. This is using the APOCA. I've realized that they don't actually have they don't have it shown in the rendering because you would see either a louver or the small round penetrations. But different design contexts. These are masonry, non-combustible construction, ranging from low rise to mid rise. This goes up to, I think this is the largest building at 6 stories. Again, passive house designed. This is actually with ICF, insulated concrete forms, basically a foam sandwich around poured concrete. So that mitigates some of the thermal bridging concerns. But again, these projects, even with the penetrations from these systems, are able to pass the strict envelope and air leakage, hopefully the air leakage requirements for passive house. We've got a bunch of projects, there are a bunch of projects that are moving forward towards construction with these. A lot of them, I'm sure, will come up across their whole building air leakage tests around the same time, and there will be a whole lot of lessons learned from these. So yeah, that's just to say, these are not necessarily just in pilot phases. A lot of projects are designing and planning to build with these at scale presently.
Thank you, Tristan, for that quick insight. And while we were giving this presentation, I also noticed that we had this discussion earlier about ground source heat pumps, but then there are 2 attendees who are sort of looking for an answer. If there is going to be a heat pump retrofit for a radiant floor, what could be the best option? And how can gas source heat pumps sort of fit in this scenario? I'm not sure if this is like within the scope of this webinar, but feel free to sort of throw some insights on this. Preacher.
I'll toss in a couple comments, I guess, on radiant floors. So in the situation I'm talking about, gas boilers, hot water, if you've got radiant floors, and typically those operate at lower temperatures than air systems, so they're easier to convert to central heat pumps, I'll say that. So right, new all electric buildings tend to use radiant heating because of that for the temperatures. So I'll say that much. As far as ground source solutions, again, on my corner, hot water systems in certain applications, those can make sense. Of course, you have to have where you can put a field, and there is risk around. You got to do it right for your ground field. So it's not an easy, simple solution, but in some applications that can make sense, especially in cold climates, where with ground source you can make hotter water in cool temperatures than with an air source heat pump.
Thank you, Peter. Jordan and Tristan, would you like to add on to this?
I don't have anything to add.
Yeah, me either.
Totally fine. And we did mention this a couple of times, I think, during the presentation, that this really works for like cold climates. So is it safe to say that there is like a sense of established market, at least for the cold climate heat pumps?
I think so.
And the scope for replicating it as well in other states?
Yeah. I mean, I think the cold climate heat pumps are part of the electrification and decarbonization solution anywhere that temps get get down, and you want to avoid electric resistance and the cost or grid concerns that come with that. And I actually have one quick question for Peter. There was a question in here about ice air technically being a VRF system, and this may get into like specific terminology and versus colloquial use. I guess I was using VRF to mean the large central VRF systems might be a colloquial term, but I think VRF strictly means variable refrigerant flow in any system that can modulate the flow of refrigerant to meet like variable heating and cooling loads. I just wanted to confirm if that's a correct understanding.
Yeah, that's my take on it. Yes. So you have a VRF system that has a central unit is distributing refrigerant to multiple zones.
Thank you, Peter. We have almost answered most of our questions in the Q&A. In case we have missed out any, we will definitely reach back to you via email. But I would like to take a moment to thank all my panelists for their time and for all the insightful presentations today. So thank you, Jordan, Peter, and Tristan. I also want to thank my colleague Shannon Wilson for coordinating and for providing tech support for this webinar. And before we wrap this up, I just want to mention that there is a survey link in the chat. Please, we'd appreciate if you could take out a couple of minutes and provide us your feedback, because that will help us bring forth even more interesting and interactive topics for the next webinars. So in case you missed out the survey link, we will also send that in our follow-up email. But thank you so much. On behalf of Shannon and myself, I wish you all a great rest of your day. Thank you.
Thanks, everybody.
Thank you all.
Bye-bye.